In the previous videos, we have been looking at the Legendre ordinary differential equation, which would have been this without the m's. So this is a generalization of the Legendre ordinary differential equation known as the associated Legendre ODE. So how do the solutions of this look? It can be shown that these solutions are given by the associated Legendre polynomials PLM, which are defined as 1 minus x squared m over 2 dm by dxm of PLX. In other words, just take the ordinary Legendre polynomials and differentiate them m times, and then multiply by this factor of 1 minus x squared. By that simple recursive procedure, you can find out all the PLMs associated to this. This is an important type of associated Legendre equation because it's useful for studies of hydrogen atoms and spin in quantum mechanics and quantum chemistry. So I just thought I'd introduce that because this is also plays into a theorem, and that theorem is that either the Legendre polynomials or the associated Legendre polynomials constitute a complete basis for the space of all real functions. Now you should think of this theorem as being on the same footing as saying that sine x cosine x, sine nx cosine nx rather, or e to the plus or minus I nx form a basis for the space of all the functions in a Fourier expansion. So just as you have a Fourier expansion of a periodic function, or even a Fourier integral expansion of a non-periodic function in terms of sines and cosines, you have a similar expansion in basis of a function in terms of either the Legendre polynomials or the associated Legendre polynomials. So that means that there is a orthonormality relationship exactly as there was one for the sines and the cosines. So the orthonormality relation for the ordinary Legendre polynomials is negative 1 to 1 PLX PL prime x dx. It's going to be some constant times delta LL prime. That constant happens to be 2 over 2L plus 1 delta LL prime. And for the associated Legendre polynomials, it's going to be PLMX PL prime MX dx. Observe that the m value is kept the same. So that's equal to 2 over 2L plus 1 delta LL prime L plus m factorial over L minus m factorial. So when m equals 0, they both agree, as they should. Now this means that anything that you used to do with Fourier analysis can now be done with the basis of either the Legendre polynomials or the associated Legendre polynomials. So let's try them. Let's try something. Let's try to do the bump function again using this new basis. The bump function is negative 1 to 1, and we want to expand it in the basis of PLX, let's say. So let this function be called f, and you would write that function f of x equals the sum from n equals 0 to infinity of an Pn. That's what expansion means. And an in turn is given by the orthonormality relationship. I'll integrate both sides with respect to, first I'll multiply both sides with another Pn. So let me do this step by step. To find ans, what I'll do is I'll multiply both sides by, say, Pm and integrate. On the other side, the summation and the integration can be interchanged if the functions are nice enough, and I get an times the integral of Pn Pm dx. I'm suppressing the variables to make writing easier, and the limits are -1 to 1. So the one restriction you do have in this subject is the range of integration, but that can always be fixed by a change of variables. So you have here the orthonormality relationship helping me. So that's going to be 2 over 2n plus 1 sum n delta mn. So I've chosen n equals m here. So if I choose n equals m, it affects the left hand side. So I get an is equal to 2n plus 1 over 2, which I can take on the other side, times the integral from -1 to 1 of Pnx dx. So that's my procedure to find the ans. Well, that's all well and good. What is it in this case? Observe that the integration limits make it imperative that we only use even functions, because odd functions will not contribute anything. So an example of an even function is a0, a2, a4, and so on. So let's actually, I'm not going to prove the induction aspect of things, and actually you can prove this using one of the recursion relations. What I will instead do is just indicate what the value would be for a couple of them and generalize from there without proof. So a0 is equal to 2 times 0 plus 1, that's 1/2, integral -1 to 1 p0 of x dx. P0 is just 1. So that's just going to be 1/2 times the integral of 1, which is x, from -1 to 1, and that's just going to be 1/2 times 2, which is 1. That was easy. A2, well, that's going to be 2 times 2 plus 1, or 5 over 2, integral -1 to 1 p2 of x dx. Well, the second Legendre polynomial is 3/2 x squared minus half, -1 to 1 dx. This is found in one of the earlier videos where we discuss the simple properties of the Legendre polynomials. You should go there to look at it. I'm just going to concern myself with showing you that this is going to be 0. So these coefficients are adjusted in such a manner that this is always going to happen for all even functions. So you can actually show a general result that the integral from -1 to 1 of all the even Legendre polynomials, with the exception of 1, is going to be 0. So this gives me 5/2. Integrating 3x squared is x cubed. So that's going to give me x cubed over 2 minus x over 2 between -1 and 1, and you see that that's going to be 0. So the upper limit is half minus half, which is 0, and the lower limit is -half plus half, which is also 0. So in this manner, and I'll write here similarly, a2m, which is the integral of the proportionality constant is proportional. I'll write proportional to p2m dx between -1 and 1 equals 0. Not very surprising, because the function is exactly 1 and the first Legendre polynomial is also 1. So we expect the expansion to have just one term. So the long and short of it is f of x equals p naught x. Now this basis of polynomials is especially useful for expanding polynomials themselves. Suppose you have a problem in which you need to expand. So here's another example of using these Legendre polynomial bases. Suppose you have to expand the function 2x squared minus 3x plus 1 in PLM forms. So what you can do is write it as an infinite sum, but you already know that you're not going to have an infinite number of terms. In fact, the first three Legendre polynomials are probably enough. So I'll write this as a naught p naught plus a1 p1 plus a2 p2. Now there are two ways of playing this game. You can use the orthonormality relation and integrate both sides and do it like that, which I encourage you to do. So basically what you end up doing is, for finding a naught, you'll integrate with respect to p naught. That'll just be the integral of that between minus 1 and 1. To find a1, you'll integrate both sides with respect to p1. The integral of p naught and p2 will disappear, and that will just give me the normalization constant. On the other side, p1 will contribute an x and increase the power of these things, and so you can find a1 and you can find a2 similarly. That is kind of a painful process. A much cooler way of doing this is to simply write down what p naught, p1 and p2 are directly, and then compare the coefficients of both sides. P naught is just 1, so that's a naught times 1, and p1 is x, so that's going to be a1 times x, and p2 I have somewhere here, so that's going to be a3 times 3 halves x squared minus a half. And now what I'm going to just do is group together terms that look alike. So a naught minus a3 over 2, that's the constant term, and then I'll group together terms that are proportional to x. So I'll also write this in ascending order of powers of x, like that. And on there's only one term that involves x, and that comes from the odd term. That makes sense, because odd degree Legendre polynomials are actually odd polynomials. P odd x are odd polynomials, and p even x are even polynomials. Notice that even includes constants. So a1 is just going to be associated with x, and then a3 is going to be associated with x squared. You have enough freedom to pull this off, because a1, a2, and a3 are three undetermined coefficients, and you have these three powers of x to the power 0, x to the power 1, and x to the power 2. So comparing, I get a naught minus a3 over 2 equals 1. A1 equals minus 3. That doesn't help you deal with this, but this will help us deal with this. So a3, 3 halves a3 equals 2, which means that a3 equals 4/3. So I have one result here and another result here, and the third result will come by substituting back in the first equation. So I get a naught minus 1/2 4/3 equals 1. So that gives me a naught equals 1 plus 2/3, which is 5/3. So therefore I've managed to write my result for the given polynomial 2x squared minus 3x plus 1 as entirely a sum of the first three Legendre polynomials. So this is going to be negative 3 p naught actually a naught comes first, excuse me. So that's going to be 5 halves p naught, 5 thirds p naught minus 3 p1 plus 4 thirds p2.